compressor. Heart of the refrigeration system today, we're diving deep into the most crucial component of any refrigeration system, the compressor. It's often called the heart of refrigeration. This remarkable device has a fascinating history and has evolved into several sophisticated forms that power everything from your home refrigerator to massive industrial cooling systems. A journey through history. The story of the compressor begins in the mid-19th century with the pioneering work of Dr. John Gorrie in 1842. Gorrie, a Florida physician treating yellow fever patients, created the first machine to make ice using a compressor-driven system. His hand-cranked compressor was crude but revolutionary. It compressed air, allowed it to partially expand while doing work, and then allowed it to complete its expansion to cool the surrounding area. The real breakthrough came in 1856 when Alexander Twining began commercial refrigeration in the United States. Followed by James Harrison's work in Australia, these early compressors were massive, steam-driven machines that required entire buildings to house them. The compressors of this era were primarily reciprocating types, using large pistons driven by steam engines. The 1920s marked a pivotal moment with the introduction of Freon by Thomas Midgley Jr. This safer refrigerant allowed for smaller, more efficient compressors that could be used in homes. General Electric introduced the first hermetically sealed compressor in 1918, revolutionizing domestic refrigeration and making it accessible to ordinary families. Understanding the mechanism, the compressor's fundamental job is elegantly simple yet mechanically complex. It takes low-pressure, low-temperature refrigerant vapor from the evaporator and compresses it into high-pressure, high-temperature gas. This compression serves two critical purposes. It raises the refrigerant's temperature above the ambient temperature, so heat can be rejected in the condenser. And it maintains the pressure difference that drives refrigerant flow throughout the system. The compression process follows the ideal gas law. As we decrease the volume of the gas, its pressure and temperature increase proportionally. But the real magic happens in how different compressor types achieve this compression. The work input required for compression ultimately comes from an electric motor, and this energy is what appears on your electricity bill. Types of compressors. A diverse family reciprocating compressors remain the most common type in residential applications. These workhorses use pistons, moving back and forth in cylinders, just like a car engine running in reverse. During the suction stroke, the piston moves down, creating a vacuum that draws refrigerant vapor through the suction valve. On the compression stroke, the piston moves up, compressing the vapor and forcing it out through the discharge valve. Modern reciprocating compressors can be single-cylinder for small applications or multi-cylinder for higher capacity needs. Rotary compressors offer a different approach, using rotating mechanisms instead of reciprocating pistons. The most common is the rolling piston type, where an eccentric rotor creates compression chambers that change in volume as the rotor turns. These compressors are quieter and more compact than reciprocating types, making them popular in window air conditioners and small refrigeration units. Scroll compressors represent a more recent innovation, introduced commercially in the 1980s. They use two spiral-shaped scrolls, one stationary and one orbiting. As the orbiting scroll moves, it creates progressively smaller pockets of refrigerant vapor, compressing it smoothly and continuously. This design provides exceptionally smooth operation with minimal vibration and noise, making scroll compressors increasingly popular in residential and commercial air conditioning. Screw compressors dominate large commercial and industrial applications. These use two interlocking helical rotors that trap and compress refrigerant as it moves along the length of the rotors. Twin-screw compressors can handle massive refrigerant flows efficiently and are capable of variable capacity operation through slide valve controls. Centrifugal compressors represent the pinnacle of large-scale refrigeration technology. These dynamic compressors use high-speed impellers to accelerate refrigerant vapor, then convert this kinetic energy into pressure through diffusers. Centrifugal compressors can handle enormous cooling loads, often thousands of tons of refrigeration, and are commonly found in large buildings, process cooling, and district cooling systems. Modern innovations and efficiency, today's compressors incorporate sophisticated technologies that would amaze those early pioneers. Variable speed drives allow compressors to match their output to cooling demand, dramatically improving efficiency. Inverter technology enables precise speed control, while advanced materials and manufacturing techniques have improved reliability and reduced noise levels significantly. Digital scroll compressors can unload capacity in precise increments by controlling scroll engagement. Oil-free magnetic bearing centrifugal compressors eliminate friction losses. These innovations have pushed modern compressor efficiency to levels that seemed impossible just decades ago. Conclusion: from Dr. Gorrie's hand-cranked ice machine to today's sophisticated variable speed units, the compressor has evolved dramatically while maintaining its essential function. Whether it's the faithful reciprocating compressor in your home refrigerator, the smooth scroll compressor in your air conditioner, or the massive centrifugal units cooling skyscrapers, these mechanical marvels continue to improve our quality of life. Understanding how compressors work helps us appreciate not just the engineering excellence behind these devices, but also why proper maintenance and energy-efficient operation matter so much in our increasingly energy-conscious world.